All right, hello, Aiden, and that's it. That's it. Aiden was gone this morning. All right. 3-1 is conjectures and counterexamples. We are in the intro to proofs time.
No. To what?
No. Proofs. We're learning proofs in chapter 3. It'll be fine. We'll be okay. Okay? Conjectures and so we're not doing proofs yet. Conjectures and counterexamples for this section. A conjecture is a conclusion. Okay? Conjectures are a fancy way of saying a conclusion. So if I give you a pattern of data or a pattern of things, you're going to draw a conclusion about it. Okay? That's a conclusion, a conjecture. And then counterexamples is proof that a statement is false. Okay? So, here you go. Here's an easy one. Shh. Proof that a statement is false. Ready? Every number is either a positive number or a negative number. Give me a counterexample. Every number is either a positive number or a negative number. Zero. Or an imaginary number, right? Those aren't positive or negative, right? So that would be a counterexample to my statement. Every number is a positive number or a negative number. False. Zero is neither positive nor negative. So there you go. All right, so let's go down here to something called inductive reasoning. Circle the word in, okay? Okay, and what we're going to do is I say we have a pattern of something, or I have a statement, and you're going to put it into a conclusion. So you take a pattern and you put it into a conclusion, okay? It's kind of like this upward inductive reasoning. You're taking something and you're putting it into some general statement, okay? In the next section, we'll talk about, in 2 sections from now, we'll talk about deductive reasoning. So it's taking a statement and then drawing information from it. So inductive reasoning, shoving everything into a conclusion, which is also called a conjecture. Okay, here's your first example for a pattern and conjecture. It says, write a conjecture that describes the pattern. So we're describing the pattern in the sequence. Then find the next term. So 2 things. Coming up with what the pattern is established, and then the next term in the pattern. So we have appointment times. They are 8:30, 9:15, 10 o'clock, and 10:45. What's a conjecture about the pattern? You're adding 45 minutes each time. That's what the pattern says. So each appointment is 45 minutes after the previous appointment. The next appointment will be at 11:30 a.m. Perfect. Okay, those 2 things. Tell me what's happening to the pattern, and then tell me what the next term is, okay? Let's do the check one right here, because this one's a little bit harder. They have 1/2, 1, 2, and 4. It took them forever to get this one this morning.
No, it isn't.
Yeah, you're doubling. You're taking it times 2. 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4, right? Because they were looking at adding. So they're like, you're adding 1/2, then you're adding 1, then you're adding 2, and they were confused. Like, what are you doing? You're just doubling every time. You're doing the same thing every time, but you're doubling, okay? So the next number in the sequence is 2 times the preceding number. The next number in the sequence is 8, okay? So we've established the pattern. We've come up with the next term. That's it. Those are conjectures. Conjecture is a conclusion. All right, let's go to the next one. We have algebraic conjectures. So this one's a little bit hard to dissect, so bear with me. Make a conjecture about the sum of the squares of 2 consecutive natural numbers. Are you confused? Let's start with natural numbers. What are the natural numbers?
1, 2, 3, 4.
Yeah, 1, 2, 3, 4, 5, and so on and so forth. Those are natural numbers. They're also called counting numbers, natural numbers, okay? And the sum of the squares of 2 consecutive. What does consecutive mean? In a row. So like 1 and 2, or 2 and 3, or 3 and 4, or 4 and 5. 2 consecutive, one right after the other. So like 1 and 2, I want the sum of their squares. So like 1 squared plus 2 squared, or 2 squared plus 3 squared, or 3 squared plus 4 squared, or 4 squared plus 5 squared, or 5 squared plus 6 squared, 6 squared plus 7 squared, 10 squared plus 11 squared, all of those, right? I want to square them and add them together. All right, so let's come up with a pattern. Let's see what we've got. 1 squared plus 2 squared. What do you get for that? 5. Okay, what's 2 squared plus 3 squared? 13. Okay. 6 squared is 36. 7 squared is 49. That is 85. Perfect. 10 squared is 100. 11 squared is 121. 221. Okay? Now, it doesn't necessarily have to be a pattern like you're adding something every time, right? Like you're adding this many every time, or you're multiplying by this number every time, right? What do you notice about these 4 numbers?
They're all odd.
They're all odd numbers. True? So we can establish the pattern that no matter what, if you add the squares of 2 consecutive natural numbers, it's always going to be an odd number. Notice that the sums are all odd. The sums of the squares of 2 consecutive natural numbers is an odd number, right? It doesn't have to be like you're adding something every time. We just notice, hey, that's always going to be an odd number, right? Happy with that? Let's go to the check. Make a conjecture about the sum of 2 odd numbers. Okay, give me 2 odd numbers. 5 and 1 is 6. You've already figured it out. 3 plus 9 is 12. 11 plus 17 is 28. Sum of 2 odd numbers is always going to be an even number, right? That's the pattern. Got it? That is called a conjecture. Okay, now we have geometric conjectures. Okay, so now they're giving me like figures, geometry figures, okay? And the thing that we're talking about is something called an isosceles trapezoid, okay? Do you guys know what a trapezoid is?
Yes.
Okay, do you know what an isosceles trapezoid is? Okay, a trapezoid could look like this. In order to be a trapezoid, it just has to have one set of parallel sides, usually at the top and the bottom, right? This is a regular old trapezoid. In order to be an isosceles trapezoid, isosceles, like, do you know what an isosceles triangle is? 2 sides are the same. That's the same thing with an isosceles trapezoid. These 2 sides, the ones that are not parallel, are the same length, right? Which is not true in just a regular old trapezoid. This one's obviously shorter than this one, okay? So isosceles trapezoid, we have those 2 sides are the same, and then we have our top and our bottom are parallel. Those 2 sides are the same, top and bottom are parallel. Those 2 sides are the same, top and bottom are parallel, okay? So that's what we're talking about. Then let's see what else they want us to address here. Make a conjecture about the relationship between the segments joining opposite vertices of an isosceles trapezoid. The segments joining the opposite vertices. That is like this line and this line. Those are opposite vertices. Okay? What's true about those 2 segments? What can we say about those 2 segments? Are they equal? Are they equal length? Sure they are. Yeah. Is this guy equal length in this one? Is this guy equal to this one? Now, if they just would have said a trapezoid, like a regular old trapezoid, would this these are called diagonals, by the way. Would that diagonal be the same as that one? No, right? We would have to have the 2 sides like symmetric, basically, in order for the 2 diagonals to be the same, okay? So, look for a pattern. Notice that the segments joining opposite vertices of each isosceles trapezoid appear to have the same measure. Use a ruler or compass to confirm this. Whatever. So our conjecture, make a conjecture. The segments joining opposite vertices of an isosceles trapezoid are congruent. That means same measure. Okay, so that's just a conjecture that we're making. We're just making a generalized statement about the pattern. Okay, questions about that? Let's move on to, another conjecture. Example 4. The table shows the average price of gasoline in the U.S. from 2010 through 2018. This makes me so sad. Meh. It got up to $3.68 in 2012. Ugh. Yikes. What happened then? I don't know what happened that year. Anyway, so it went up, then it went up again, and then it went back down again. So at $3.68, this is like a maximum amount. Then it's going back down and down and down, and then it hit a minimum amount. And then it's going up and up and up, right? They want us to make a conjecture about what it would be in 2019. You have any ideas? You want to take a guess?
I think
We Googled the price.
What?
I think it'll be like higher than.
You think it'll be? So we guessed this morning. We said, okay, 284 is the same in 2010, so maybe it'll like history will repeat itself and it'll be back up at 358. So we said that. And you know what they said? Conjecture, in 2019, the price of gas will continue to increase. I thought they wanted some specific amount. They don't. They just want the conjecture, the overall generalized statement saying, hey, it's going to be higher probably this year because it's on the upward trend, right? The data shows that the price of gasoline is an oscillating. Do you know what the word oscillating means? To oscillate. It's doing this. This is oscillating. So it's going up and down. So price of gas is doing that, okay? Now, I would guess that actually the price of gas is going to do more of this pattern. Why? It's still going to oscillate, but why? What? Inflation, right? Yeah? So I would guess it would oscillate, but probably do more of that pattern overall, increasing over time, okay? So they kind of like cheaped out and said, instead of giving a specific amount, they said it's just going to increase. Generalized pattern, okay? All right, let's go to counter examples. Counter example. A counter example can be a number, a drawing, or a statement. Okay, so I said every number is a positive number or a negative number, and you're like, nah, not zero, right? It's anything that can prove a statement false. Okay, so let's show this counterexample. Find a counterexample to show that each conjecture is false. A says if n is a real number, so n is a number, any old number, then negative n is a negative number. So they're assuming, like, let's say 3. If 3 is my number, is negative 3 a negative number? Yes. Let's say like 7. If 7 is my number, is negative 7 a negative number? But is that always true? What is a counterexample? Let's say negative 1. If n is negative 1, right? If it's negative 1 to begin with, negative 1, is that also negative? No, that's going to be positive. So for my counterexample, I'm going to say n equals negative 1. Okay? Now you could list me a ton of them. They chose negative 4. You could have chosen 0, right? 0 is not negative. So that would work, but you only have to list one thing in order to prove the whole statement false, right?
What classifies something as
A real number is any number. Decimals, everything. Every number is a real number except i's.
Oh.
Yes. So a real number is like pi even, or the square root of 2, or any number that has decimals, fractions, anything. Anything is a real number except I, which are imaginary numbers, right? Real and imaginary. All right, next one. This is kind of hard to see. So they have ABC is an angle, and DBE is another angle. Now notice that they have B in common, so they have to touch each other at B. And it says that those two angles are the same. And it says ABC and DBE are vertical angles. So what they're trying to get the picture in your brain is that it looks like this. A, B, C, and D, B, E. And we're talking about this angle versus that one. It's saying if those two angles are the same, they have to be vertical angles, right? Could those angles be set up so that they are this equal measure, but they're not vertical angles?
Yes.
Like this, right here. They share B, but we're talking about this angle here and this angle here. Are those two angles the same measure? Yes. Are they vertical angles? No. So in this case, my counterexample is this drawing. My drawing equals my counterexample. All you have to do is be able to draw or write or give a value that proves it false. Got it?
So it's something that's not.
It's something that makes it not true. Yes. Yes. Okay. This is like lawyers do this all the time. Okay. So up on the stand, they have somebody like coming to testify or whatever. And what they try to do is if they have somebody coming to testify against you, your lawyer gets up there and says, they try to put the person on the stand and ask them questions to make them look less credible. So if they're able to put the person up on the stand that's testifying against you, and if they're able to make some sort of statement to say that they're lying one time about anything, then it makes them look not credible anymore as a witness, and then they basically can discredit everything that they've said, right? Do you see what I'm saying? Does that make sense? Okay, so it's like making a counterexample. We only have to do one thing that makes that person look bad, and then basically everything that they have to say is a lie, and then I have a better defense. Does that make sense? Okay, so kind of that type of thing. If we're using logic and reasoning and that stuff, think of it in the court system. Just one counterexample, one thing that proves what they're saying is false, and then we can just discredit everything else, okay? So, again, a counterexample could be a number like we had here. N was -1, you said. It could be a drawing or it could be a statement, right? Okay, so any of those things could be a counterexample just to prove that something is false. Done? That's it. 1 through 13 odd, 18 through 22 even. Perfect. Okay, goodbye.